water webinar series. In the first one, we had Dr. Sidhu and Dr. Rajput. They spoke mainly on conservation agriculture as well as how to use the surface irrigation instrument IoT, what is required, that type of topic. Second day we had Chandrasekhar Patsaule, who talked about no tillage farming mainly and to enrich the soil as well as water. And he reported about high yields after several years. And we also had Ravi Pratap Singh. He told that we have to gear up for implementing the water saving technique. So how to use the entrepreneurship to implement. In short, I'm not trying to review what they told. And today we have excellent topic in the same direction. We have a more scientific topic. Both of them are experts and well recognized in their area. So we will first invite I'll ask Dr. Viswanathan to introduce the first speaker. Rakesh Sharda, please. Dr. Viswanathan?
Yes, sir. Thank you, sir. Dr. Rakesh Sharda started his professional journey with the PAU Ludhiana in 1996. He has been actively involved in research, extension, and teaching activities related to micro irrigation, protect cultivation, and using non-conventional energy resources in irrigation. He also worked in the areas plant factories, aeroponics, and aquaponics. Dr. Sharda has developed 28 technologies related to drip irrigation, fertigation, and mulching of various crops, and evaluated a mulch laying bed farming machine and a vegetable seedling transplanting machine. He was involved in developing a modified poly net house, rooftop kitchen garden, soilless cultivation of cucumber, and rational use of poor quality water through drip irrigation. These technologies are included as part of the package of practice for farmers. His current research areas focuses on artificial intelligence in water resources and IoT in agriculture. Dr. Sharda has completed 22 research projects with a total funding of about 46 crore rupees received from various funding agencies. Also operated by consultancy projects in micro irrigation, protected cultivation, and rainwater recharge. Dr. Sharda has executed an assignment at FAO as an international soilless and protected cultivation expert. He adopts multidisciplinary approach involving crop scientists and engineers of the other discipline. Dr. Sharda has published 85 research papers in reputed national and international journals, besides several technical bulletins, popular articles, books chapters, and symposia papers. He has guided 8 MTech students and 2 PhD scholars as major advisor and as also advisory committee member for more than 40 postgraduate scholars. Dr. Sharda is an active member and fellow in many professional societies and currently the chairman of the ISAE Punjab chapter. He is member of various state and national committees on micro irrigation, protected cultivation, and solar photovoltaic pumping system. Dr. Rakesh Sharda was the head of the Department of Soil and Water Conservation Engineering, PAU Ludhiana, during 2023. Currently, he is the project coordinator for the All India Coordinated Research Project on Plastics Engineering and Agriculture Structure and Environmental Management at ICAR CIPAT, Ludhiana. Dr. Sharda is the Chancellor's nominee at Punjab University, Chandigarh, and also member in the Research Advisory Council of the National Innovation Foundation and a lead member in many sectional committees of Bureau of Indian Standards. Today he is available with us to share his experiences in mechanization and automation for irrigation water management. On behalf of our team, I welcome him for this presentation. Thank you.
Thank you, Dr. Saab, for the nice introduction. Shall I start?
Yes,
Share
please.
my screen. Yeah, thank you. I think my presentation is in slide mode. It's
Yes,
visible to
very
all.
good. Yes,
Thank you.
yes.
So, respected seniors, Dr. Gajendra Singh, Dr. Rajput, Dr. Kanwar, Dr. Taneja, my teacher also, and Dr. Ismail, and many others, Dr. Srini, and a lot others. All are my seniors and respected seniors. Today I've been asked to deliver a lecture on water saving technologies, a step towards sustainability. Well, when we talk of water, it's the elixir of life. When I say elixir of life, everything, every every part is made up of water. And if we start from the cell, so cell is about 70% of the water. And without water, we can say there is no life. And even in plants also, it's the water that translocates minerals and then the food to the different parts of the plant. I'll not go much into it. But then if we go by uh, this FAO sayings, they say that it takes 2,000 to 5,000 liters to produce a person's daily food. And the requirement of the person for drinking is only 3 to 5 liters, not more than that. And you add some more to it, so it becomes around, if you say in urban India, it's around 140 liters per day per person. And but for the food, he requires at least 2,000 to 5,000 liters of water daily. And of course, water use efficiency is increased globally by 20%. But then 50% of the reported countries still exhibit low water use efficiency. Even in our country, the water use efficiency is not more than 40%, very, very low. And of course, 70% of all the withdrawals in the world is for agriculture only, whereas in the case of in the case of our country, it is more than 80%. And if I talk about Punjab, it is around 94%, which we are using for uh, irrigation only, or using for agriculture only. And of course, the rising water stress in affecting foods is affecting food security and biodiversity. And in 2023, over 864 million people experience severe food insecurity, periodically going without food for an entire day or more. And between 13 to 757 million people were undernourished. And leave aside the basic sanitation, they don't have access to a good drinking water, good water quality for drinking purposes. And of course, if we talk of our country, between 1950 and 24, India has seen a decline of 73% in per capita surface water availability. And of course, if you see this, this is 2025, only few of the pockets. It's the northeast part and some part in Kerala, which is under no stress. And same will be the case when it will be in 2050. But in the rest of the country, there will be there will be stress to absolute scarcity of water. And of course, just imagine that the way our population is increasing, how we are going to feed those billions. And of course, groundwater used for agriculture in India is around 213 BCM, and out of that, 208.4 BCM is for agriculture only. And just take an example of Punjab. Around the total water demand is around 66.12 billion cubic meters, and agriculture contributes. Agriculture share is around 62.58 billion cubic meters, and the water available is around 52 billion cubic meters, and the deficit is around 13.27 billion cubic meters. And this deficit is met from uh, exploiting the groundwater, the lower aquifers, and we are exploiting it like anything. But if we increase the efficiency, say the efficiency is increased by 10%, just by increasing the efficiency, water use efficiency, we can we can be water surplus. As you can see, almost just by increasing the water use efficiency by 10%, we will be water surplus by 2.37 BCM. Now the challenges. The challenges are food security, climate change, flood and droughts, urbanization and conflicts. And all these are related to water only. When I say food security, it's an axis. When I say water, the water has an axis with food security, climate change, floods and droughts, urbanization and conflicts also. And of course, as I've already told you that in case of food security, just to have the food security, we require at least 2,000 to 3,000 liters of water per day to meet the food requirements of the individual. And you can just imagine what will happen if we keep on if this keep on declining. And if I go to sustainable, if we talk of sustainability, water sustainability specifically, improving efficiency in the use of resources is crucial to sustainable agriculture. And water is that, and the water is most important of that. And water is rather more critical. And sustainability requires direct action to conserve, protect, and enhance natural resources. Agriculture that fails to protect and improve rural livelihoods and social well-being will always be unsustainable. Enhanced resilience of people, communities, and ecosystems is key to sustainable agriculture, and sustainable agriculture requires responsible and effective governance mechanisms. So when we say that agriculture has to be sustainable, the first thing that comes to our mind is that it must be water sustainable. If there is no water, there will be no life, and that is the apt statement. And of course, when we talk of water saving technologies, so I categorize these water saving technologies as the first thing is the measurement of water. The second thing is irrigation scheduling. And the third thing is whether I want my water to go out of my ecosystem. No. So my area, my water, efficient irrigation methods, crop genetics also plays an important role in water saving technologies. And of course, use of disruptive technologies. I'll go one by one. So one is measurement of water. Effective irrigation water management begins with accurate water measurement. Even today, when we say that almost 60% of the area is irrigated, we talk like this that okay, if the farmer is applying water, we give him the thumb rules. Okay, you can go for 4 irrigations for wheat, some around 13 to 14 irrigations in case of paddy, and similarly for all other crops. And then comes the usage of uniform units of water. Till today, we say that okay, the water is measured in either in depth units, or we like any other. We still use age-old systems of units. Why not liters of water? We must say that, okay, water is this much liters of water you have applied, and the farmer will be able to connect with the systems in a better way, because he knows that when he goes to the market and buys a bottle of water, it costs rupees 20, around rupees 20, and that is the cost of the water, and that is the water he's putting it in his fields, in his or her fields, and that is what he is exporting, the blue water. And then comes the usage of water measuring devices. We must have water measuring devices at our systems. And then also comes the usage of efficient equipment. And of course, efficient equipment will also help us in saving the electricity and saving the energy, as well as having more efficient water supplies. And of course, when we talk of irrigation scheduling, so we are working on soil water measurements, maybe soil water content, soil water potential, soil water balance, entering and outgoing water fluxes, then plant water stress, another methods. But do my farmer needs such complicated methods? The answer, for some, it may be yes, or for some, it may be no. When we say yes, so it means we are investing more. But in our part, we cannot say that a farmer can invest that much money on these systems. So we have to come up with the systems. We have to differentiate. Okay, these are the systems to be used for the research, and these are the systems to be used by the farmers. So when we talk of it, so when we talk about this, so we come up with a sorry, I'm receiving one call. I just switch it off. Okay, the flow chart of decision support system for on-farm irrigation water management. Now the thing is, if I can get the idea of evapotranspiration, reference evapotranspiration, mixing, multiplying it with crop coefficients, and I can easily tell my farmer how to apply. But till today, we are saying telling him, okay, you apply 4 irrigations for, and that is for Punjab. 4 irrigations in case of this. So we developed an idea that let's come up with a decision support system where, based upon the meteorological data, we can find out the things. But then, of course, this is a schema of things, how it can be done. And then, of course, this is the best formula. We say that, okay, this is the best method of computation of ET naught. But then there are a lot of parameters into it. And ultimately, we end up with the empirical equations only. And we say that, okay, this is fine. Some 70 to 80% of accuracy can be achieved with such a method, and we go for that. But then AI and ML gives us another opportunity. We can now have the algorithms. If we have got the data, we have got the algorithms which can accurately, yes. We can accurately tell about the water deficit, and that can be easily incorporated into the decision support system I have shown to you. And then we can apply, the farmer can apply the water and take the decision of irrigation based upon that. No requirement of any sophisticated sensors or equipment for that. And these systems can be easily integrated with the automated systems available in the market. So we did some study on this. We said, okay, we take up the different scenarios for almost 5 districts of Punjab with these parameters. We use the AI. 70% of the total data was split into training, and then we found out. And you see, estimation of, we did it for 5 different zones of Punjab. And this is the performance evaluation of ANN model under different scenarios for Ludhiana. Similarly, for different scenarios of Ludhiana. And then we tested, and we find that there is a very strong correlation between the developed model and with even with the minimum of the parameters, the accuracy up to 92% it can be achieved, and that is fairly good for my farmers. You can see this the value of R here, the value of R from even with only two parameters, that is minimum and maximum temperature. We can leverage these technologies for our predicting the irrigation requirements of the different crops, which was not earlier can be done with the help of such an accuracy was not available with the empirical models. And then, of course, my area, my water. It means that I am not going to make the water flow out of my system. If it is my district, it is my water, whatsoever we are extracting, it is into a circular economy of the water. Whatsoever I am getting as a rain, that will be utilized, and ultimately it will be like nothing is going out of my, or almost we can say that zero is going out of my district or my area. And we have to come up with such approaches so that we can manage our resources, water resources in a better way. And of course, we have to transit from linear economy of water to circular economy, where we say, okay, we abstract the fresh water, natural flows are there, diverted flows, storage, supply systems, water use, and then let it outflow from our system. And that becomes also a havoc for the people who are living downstream. As in the case of Punjab, whatsoever water that is moving out of, say, on the districts on the upstream, that water is going downstream. Ultimately, we are polluting it, and that is being and the people are utilizing that water for agriculture as well as for drinking purposes. And see what is happening. But then, of course, system with the circular thinking, circular economy of water thinking, it means everything that it has to be remain within the circular part only. And then comes the efficient irrigation methods. It may be micro irrigation systems. It may be alternate wetting and drying methods of irrigation in paddy. It may be conservation tillage, as has been discussed by Dr. Sidhu earlier. And then, of course, automated irrigation systems, because such systems will help in saving water. And if we talk of water saving technologies, water saving and yield increase using dip fertigation. So we worked a lot on this. We started a focused approach. Our university started a focused approach on this. And at present, we've got technology, drip irrigation and fertigation technologies tested, evaluated, and part of the package of practices of the university, Punjab Agriculture University, and almost you can see almost all the crops, all the major crops, even wheat, and people have worked on wheat and paddy also, and we have also demand for for agroforestry crops. And you can see there is a water saving. This is a known fact. I don't have to delve on this. And then, of course, we have to come up with the disruptive technologies also, because in this part of the world, we cannot say that okay, we can change the whole land into micro irrigation, and suddenly one day we'll find that a lot of investment is required and nobody will go for it. But then we have to come up with the technologies which are which are low cost, and of course applicable in the field. And one such technology is low flow, low pressure drip irrigation system. In earlier drip irrigation systems, we require a head of at least 10 meters. But for this system to work, the head requirement is only 60 centimeters. And the only requirement is tabletop lands. And particularly in the areas like flatlands Punjab or Haryana, these systems can be easily employed. But then there are some other problems regarding its standardization and all that, but that can be looked into, seeing the benefit of the system. Normally, the drip irrigation system, if we go for in paddy or wheat, in paddy and wheat rotation, the cost is around rupees 2 lakh per acre. But then this system costs only 60,000 rupees per acre. And then no filtration system is required, no investments on filtration system, no requirements of changing your pumping systems, like in our part of world. In our part, these whenever we say that, okay, go for micro irrigation, the first thing that comes up is the most of the pumps that are being used in our state are low pressure, high discharge pumps. But then here that will not be the case. And so in this case, we don't have to modify even that also. And we can easily irrigate any number of area depending upon the size of the pump. And of course, energy saving is 100% in case of canal irrigated, because in canal irrigated, we normally provide a head of 1.5 to 2 meters. And these systems can be easily integrated with those. And in case of in case of if we are using electrical energy, it means the water saved is the energy saved. So it's no external energy source can be required, and it is a very simple installation, and the systems are available in the market. This is the crop on wheat crop on low flow, low pressure drip irrigation system. Then, of course, drip irrigation in paddy. In Punjab, India, exploring the new horizons. We can raise paddy on drip irrigation system. Earlier, we were using we started with using sprinkler. Then we shifted to drip irrigation system. We devised a strategy where we for first 20 days we manage the crop using flood water, and then we shift it to drip irrigation system. Now what we are doing is we go for puddled rice, and the moment the crop sustains, say after 10 to 15 days, we go for we already recommend alternate wetting and drying system. So in place of alternative wetting and drying, we say, okay, go for drip irrigation system. And these systems save around 48% of water in case of DSR. And if we are using this system in puddled rice, then we save around 34 to 36% of water, and there is no penalty of yield. That is the USP. This is the crop at my place. We did experiments on this crop on paddy. I'll not go much into it. And of course, 25% is the energy saving if we are using. Now I say there are two type of systems. One is conventional drip irrigation system, and the other system is low flow, low pressure drip irrigation system. In case of conventional drip irrigation system, we save 25% on energy. But in case of low flow, low pressure drip irrigation system, amount of water saved is the amount of what energy saved. It means if 36% is the water saving, it means 36% is the energy saving. And in case of DSR, if 48% is the water saving, it means 48% is the energy saving. And during 2009 drought, the central government provided 900 crore subsidy for diesel for paddy crop. And that is, and of course, we get higher yields during the drought periods. And of course, this is another trial done by our university, alternate wetting and drying. It saves around 20% of water. And then comes the crop genetics. I'm almost finishing. Development of drought-tolerant varieties. Of course, people are working on it. And then university gave another variety, short duration variety of paddy, PR126. This is a short duration variety which can be harvested in 90 to 95 days. And it means, and if we add the other period of nursery raising, it means 123 days, 125 to 30 days. Whereas in the case of other varieties, particularly the Pusa variety, this duration is around 140, 160 days, 160 to 170 days. And that means higher guzzling of water. And that's why this year the Punjab government has banned transplanting of Pusa 44 variety. And then, of course, the disruptive technologies, Internet of Things. We are not, earlier we were like taking data only for 2 times a day, say for temperature, and we were running our models and we were saying that, okay, my model is predicting perfectly. But now with the advent of these technologies, particularly at the low cost, the thing that matters is the cost. Because of the availability of these technologies at the low cost, now I can have a data of say temperature, humidity, and moisture content, and light intensity, everything every 5 minutes or even every second. It means I will be able to relate this data with my plant growth in a better fashion. And of course, this in combination with machine learning and machine learning analytics and artificial intelligence will certainly help me in getting in having a better understanding of the systems. And then of course drones and crop monitoring. Nowadays we are working on a university is working on micronutrient deficiencies measuring through the drones. We are working on measuring developing models or decision support systems for finding out abiotic stresses of the crop through the image sensing systems, and of course farming robotics and autonomous transport systems. Recently, this Central Mechanical Engineering Research Institute has launched a EV tractor and electric tractor and electric tiller in the market. And of course, we can have these remote controlled sensors or control of valves. Like earlier, we were using wired systems. Those systems can be replaced by the RFID systems and or RTUs. And then another technology that is vertical farming and hydroponics. Of course, this is one such technology where we say that, okay, we can save up to 95% of the water. Only 5% of the water is required. And and of course, till date, we say that, okay, a lot of energy is required for these systems. But then I am very hopeful that one day these technologies will be less energy intensive, and these can be, and of course, low inputs are required in these systems. And moreover, I tell you, we are working on in a plant factory where we can have 11 cycles of lettuce production. Whereas in open, it's only two crops in a season, and that too during winters only. But when we are doing it in the plant factory, it is like 11 cycles, and with a better quality produce. And of course, these things can also be combined with these combined with specialty nutrients. Like for kidney patients, we say that, okay, low potassium diet is required. That can be easily managed with these systems. And with this, I finish my presentation. Thank you for patiently listening.
Thank you.
Open for questions.
Thank you, Dr. Sharda. Dr. TBS Rajput, you raised your hand.
Yes. I compliment Dr. Sharda for very systematically presenting the whole issue and very comprehensively covering that entire flow. of the whole saving of water. But Anna, there are certain realities of Punjab, and I think you are very much aware, and we are discussing it on NAS group. Nowadays, Dr. S.S. Kukal and Dr. B.S. Dillon, both are very worried that this government has preponed the transplantation date of rice
Very
by
low.
15 days or so. Now, that is something different. Now, central government you just mentioned has also given some money for diesel use. Where are we leading to? Electricity is already free. Water is already free. So all the system of the technologies that we are developing or that you are developing and that Dr. Sidhu spoke, how can we find these things happening in Punjab? So I'm talking to you because you have a strong voice there. So do you have any mechanism in mind, or would you like to discuss with me tomorrow? Are you coming for that meeting? I'll take time and discuss with you. Thank you.
We'll discuss tomorrow, but then I
Yeah.
just add to it. Punjab is right now, Punjab is the only state which does not have any focused platform for micro irrigation. So now we are requesting the government, and we are in active parleys with the government also, that let's do the same way the other states have done and invest more into micro irrigation. At least the 8 lakh hectare areas, that is around 25% of the total cultivable land, particularly in the case of these fruits, vegetables, then cotton, and then comes the sugarcane. And of course, actually, I will not comment on the political pressures, but then of course the one thing, the one positive thing that has happened is banning of Pusa 44 for cultivation in Punjab.
Thank you.
Rest we will
Thank
discuss
you.
tomorrow.
Thank you.
Thank
Dr. Gajan Singh. Dr. Gajan Singh, please.
Yes, Dr. Sharda, I'm
Yes, sir.
interested in this low flow drip irrigation system. You said it requires only 60,000 rupees per acre
Yes, sir.
and only 60 centimeter head. How much area have you tried on? And
Sir,
which crop?
for my experiments, I did trials in around 2,000 square meters, but then we worked with the farmer also around 3 acres, and then of course around 150 acres of farmers are doing this with the help of Pepsi and NDRIP. And of course, these systems are available through NDRIP, Israel, and then Jan Irrigation Systems Limited, Jalgaon.
Yeah, it's quite encouraging. Thank you.
Thank you. Dr. Uday Kodke.
Yes, thank you. Am I audible?
Yes,
sir.
yes, go
Yes,
ahead.
yes.
Hello. This is a good initiative in the state of Punjab, and the research being conducted by the team of irrigation water management. In fact, the use of drip in rice cultivation was initiated in Tamil Nadu, and they have very encouraging results. Another point is regarding the low flow, pressure system, as Professor Gajendra Singh sir has already raised that. I am doubtful about the uniformity coefficient and other parameters, what you observed. Actually, I would like to discuss with you. In Parbhani, in AICRP on IWM, we use the Pepsi drip and we evaluated for 5 years.
Okay.
The cost evaluation, BC ratio, was not comparable with the conventional drip because farmers were also using that time. Even the KVK, Jalna, many KVK, they adopted this Pepsi irrigation, and that too for the vegetables and other crops. But then the cost economics was not encouraging in case of Pepsi and that low flow, low pressure system. What is your opinion and what are your observations? That I would like to know, please.
Sir, actually, when we talk of low flow, low pressure drip irrigation, low pressure drip irrigation systems, the idea that comes to the mind is like having a tank fitted at a height of say 5 meters or 6 meters and covering an area of 1,000 square meters. But that's what happened with me also when somebody promoted the idea to me. So, but in this case, it's the amount of discharge that matters. If you are having a discharge of say 16 LPS and you can manage that discharge in the through the pipes, there's no problem of uniformity coefficient, nothing, as long as it is the tabletop lands. If the lands are tabletop, there's no problem of uniformity. Everything is perfectly all right. And of course, when we talk of low pressure drip irrigation system only then there is a problem. But in case of low flow, low pressure drip irrigation systems, they have devised the their drippers in emitters in such a way that the problem of uniformity is not there. And of course, I can share the data with you afterwards.
Thank you. Dr. Indramani?
Thank you, Dr. Sharda. My question is actually similar to Dr. Rajput, but I want just to suggest that in Maharashtra, the state government and the universities work very closely. So is there any mechanism in Punjab that how much universities consulted or, so if not, then you should we should raise this point from some platform.
Sir,
That,
I
because
answer to that.
Maharashtra is facing, that Marathwada, Vidarbha face water problem. So water related definite programs, state government consult university. Without consultation with university, they don't implement. So similarly, because you know that Punjab problem is not new. 1991, Dr. Sinha, under Dr. Sinha, late Dr. Sinha, a committee was formed and which recommended that take immediate action, otherwise half of Punjab will be saline and half of Punjab will be without water, and that situation has almost come. So there is, now the situation is of, alarming. So Dr. Rajput, because he is discussing with this one, in NAS also, probably some strong message should go that university system must be consulted when they are taking agriculture related decisions.
I reply to that, sir. Regarding this, particularly the we are like we work in close unison with all the state government departments. Then the problem is not just working with the there are no differences between the state government and the university. State government departments, I would say, not state government. The state government departments and the university, they work in close unison. But then the problem is something political. And that I'm not going to comment.
Avoid that topic.
That I'm not going to comment. I tell you, even for protected cultivation, I'm there as chairman of panel empanelment committee as well as design committee. And I am part and parcel of Department of Soil and Water Conservation. And similarly, the people from the Department of the College of Agriculture, plant breeding, they are all part and parcel. They always interact with the state government people. They release the varieties in close unison. But then the thing is, we are not going to decide when the paddy crop has to be sown or transplanted.
That's sad.
That's
Dr.
my
Pitam-
take on that.
Yeah,
All
that's
right,
really
all right.
great.
We understand.
Dr. Pitam Chandra, please.
Yeah, just a quick question, Dr. Sharda.
Hanji,
What
sir.
is happening with SRI? We used to talk a lot about SRI a few years ago. Where is it now?
SRI, we talked a lot about, but then SRI was like is very labor intensive and input intensive, and I think nobody has taken it up in our region. And similarly is the case with wherever it has been done, it has been done at a very low scale.
Okay, thank you.
Thank you. Thank you very much, Dr. Sharda. It was very interesting
Welcome
and
to you.
enlightening for all of us. I'd like to invite the next speaker, Dr. Viswanathan. Can you introduce the next speaker, please?
Sorry,
Yes,
can
sir.
I ask some questions? Sorry. Hello.
Yeah.
Namaskar ji.
After he finishes, we already start the second topic. After you speak, you can ask the question. No problem.
No, I would like to ask Mr. Sharda, Dr. Sharda.
Yeah, you can ask him. He'll be
Dr.
available.
Sharda will be here.
Please.
And,
He'll be here
yeah.
available.
Okay.
Don't worry.
Good,
Please
good,
go
good,
ahead.
good, good. Thank you. Thank you. Good.
Dr. Viswanathan, go ahead.
Yes, sir. Thank you, sir. So let me introduce next speaker, Dr. Srinivasulu Ali. Dr. Srinivas is a professor of agrohydrology at the Texas A&M Agri-Life Research Center at Vernon, United States of America. He is also affiliated to the Department of Biological and Agriculture Engineering at Texas A&M University, College Station. He obtained PhD in Agricultural and Biological Engineering from Purdue University, West Lafayette, USA. MTech in Irrigation and Drainage Engineering from GB Pant University, and BTech in Agriculture Engineering from Andhra Pradesh Agriculture University in 1989. He started his career as assistant professor at Acharya N.G. Ranga Agriculture University and served for 12 years before moving to United States for higher studies. He has extensive experience in hydrologic, water quality, and crop growth modeling. His research programs focus to develop and evaluate climate resilient regenerative agricultural strategies for conserving soil and water, enhancing crop water productivity, and protecting soil and water quality in diverse agro ecosystems. He has operated externally funded projects worth over 23 million US dollars. He has advised 9 masters, 7 PhD, and 11 postdoc scholars. He has published 106 papers in reputed journals, articles, and 4 book chapters, and delivered more than 200 conference presentations and 35 invited talks. His publication has more than 3,000 citations with the H index of 33 and I-10 index of 71. He is a fellow of the Indian Water Resources Society and Indian Association of Hydrologists. He is a life member of the American Society of Agricultural and Biological Engineers, ASEAN Association of Agricultural Engineers, and ISAE. He has served in various leadership roles in ASABE, including as Technical Program Chair of Annual International Meeting in 2023 and 2024, NRES Community Chair, and the Texas section of ASABE and its chair. He is currently serving as the Vice Chairman of the ASABE Meetings Council. He has received several awards, including the ASABE Educational Aids Blue Ribbon Award, ASABE Texas Sectional Agricultural Engineer of the Year Award, ASABE Superior Paper Award, ASABE Outstanding Associate Editor Award, and many more. And he has been recipient of Student Award at Purdue University for his outstanding PhD work, and also a gold medal at Acharya Ranga Agriculture University for his undergraduate program. So today he is giving a presentation on simulated efficient irrigation strategies for sustaining crop production under declining water availability. So I welcome him on behalf of us for this talk. Thank you.
Um, Thank you, Dr. Vishwanatha, for your kind introduction. Yeah, I would like to, first of all, thank, Dr. Ismail and Dr. Vishwanathan for giving me this opportunity or inviting me to talk, to this August audience. And it's really a great honor, to be able to share some of our work in front of, eminent agricultural engineers who are attending this webinar. So once again, I mean, like this is mostly focused on, our studies we conducted in Texas High Plains and Rolling Plains regions. I know this webinar is focused on Indo-Gangetic, plains, but these strategies that we develop here, for this study region can also be developed, for Indian conditions. So I just thought, I will share some of the ideas, that way, we'll be happy to, collaborate with anyone who is interested in doing, such studies in India. So with that, I just want to, say a little bit about my program and, our system here. This is the state of Texas, and this is where College Station is located, where the Texas A&M University main campus is located. And we have about 13 research centers, like, more like RARS in India system. And we are here at Vernon, which is almost like, close to the Oklahoma border, and about 380 miles, from College Station. And then the smaller ones are, additional, satellite research stations in our system. So the goal of my program was already told in my introduction. Basically, we conduct research, mainly focused on sustainable management of land and water resources under changing climate. And we carry this in, 5 different areas, starting with, land use change and grazing management impacts on environment, development and evaluation of efficient irrigation strategies and decision support tools. My talk today will focus on this aspect. We also did quite a lot of research on climate change impacts on crop yield and adaptation strategies. I did a lot of work initially when I joined here on groundwater quality and quantity, say spatio-temporal variability assessment. And then currently we are doing a lot of research related to regenerative ag focused on improving soil health and ecosystem services. Basically, as was told in the introduction, I'm a modeler. We use extensively the hydrologic water quality models, biogeochemical models, crop growth models, and we have started using, machine learning based approaches, and then, efficiently use, UAV based measurements for addressing some of the science questions in our recent, programs. So first of all, I would like to, thank my research team and my collaborators. So this is really a teamwork. I acknowledge, some of my current and former, team members, including, Sayantan, who is currently a postdoc, Sushil, whom you might have met last year at the AAE conference in Bangkok. He is currently a faculty. He worked as a postdoc for about 3 years in my program before going there. And then Kritika, is a faculty at IIT Roorkee. She was my second PhD student. And then Chong, Bhupinder, and Jasdeep, they also, worked with my program, and they're currently, either faculty or research scientists in other universities. And these are my collaborators from, A&M, and also, some of them from outside, including, Ed Bonds, who really supports my modeling programs. He's with the Cotton Incorporated. So as I said, so my talk will be focused on the Texas High Plains and Rolling Plains regions, which are shown here in this map here. So these are very, very important agricultural regions in the United States, especially the Texas High Plains. The southern portion is heavily irrigated, with the Ogallala Aquifer, and in the Rolling Plains, where we are situated, much of the production takes place with the water from the Seymour Aquifer. So these are primarily, groundwater dependent or rain-fed, systems, especially in the Ogallala Aquifer region in the Texas High Plains. The major challenge has been, rapid decline of water levels due to extensive, pumping, which is much higher compared to the recharge. These are semi-arid regions. This region receives around maybe 15 to 20 inches of water precipitation, and then this region receives about 25 inches of precipitation annually. So which is much less to recharge water compared to the irrigation withdrawals. And keeping this in view, the groundwater conservation districts in this Texas High Plains region started imposing restrictions on a producer can only pump about 18 inches of water a year. He can bank and then use in the later years, but in a typical year, they do not allow pumping more than 18 inches of water to sustain or extend the life of the aquifer for the future generations. In addition to this declining water availability, the climate change studies project much warmer and drier summers in these regions, which necessitate more irrigation water application to meet the crop ET demands. So therefore, adoption of innovative strategies is critical for sustaining crop production in these regions. So our thinking was, we are quite familiar with the deficit irrigation strategies with, different percent ET replacement, like, 80% ET replacement or 90 or, like that. So instead of replenishing the entire ET, we can, apply some kind of deficit and then can save some water. And then there are also, some strategies focused on crop growth stage-based irrigation because crops have, different irrigation requirements in different growth stages. So if we can manage, applying less water in the, less critical stages and more water in the more critical stages could save, some irrigation water there. And then Sushil actually came with, this novel idea, that can we combine these two? Like, can we apply differential ET replacements in different growth stages, which would, further enhance, the irrigation savings. So that was a great idea. And then we implemented it in corn and sorghum. And now we are moving into, cotton and sorghum. We are moving into corn also. And then Sayantan came out with this additional idea like, can we, apply, priorities, whether the goal is to increase yield or to save water or both. So accordingly, can we, devise these, deficit irrigation strategies? So that was the thinking process. And then we also, parallelly, worked on developing a mobile app for irrigation water application. So that also I would like to cover, briefly. And all these studies, the crop growth models are very useful. They can be rapidly or inexpensively. They can simulate different irrigation strategies, and then we can do some comparisons and what if scenarios can be run, and then they're very useful. So our work primarily used the DSAT cropping system model, which is quite popular in a cropping system model. It basically a platform that integrates crop models, database management system, and various applications. So the recent model, actually, it's 4.8.1 also came out, and then there's more than 42 modules, for different crops. And some of the modules that we used are for cotton, sorghum, and wheat. Basically, this model uses, weather, soil, cultivar, and management data to simulate, crop phenology, crop growth, crop yield, while also simulating, soil, water, carbon, and nitrogen, balances. So it's a very good model, and then we have been extensively using this model in our, these modeling work. So first, I will talk about, the crop growth stage-based deficit irrigation strategies for cotton that we developed. As I said, Sushil, led these studies actually while he was working with me. So once again, like if you look at cotton, we primarily have, categorize 5 different growth stages, and then they have, different levels of irrigation requirement in those growth stages. So what we did is, we did a hypothetical experiment in which, we thought, okay, if a farmer has, 240 millimeters of water until up to 480 millimeters of water, how best, the farmer can, distribute this irrigation water to different growth stages. That was the focus. So for each of these scenario, we had 6 different, treatments. In the first 5 treatments, we did not apply irrigation water in one of the growth stages. And in the 6th, the treatment, we applied irrigation water in all growth stages. But remember, in all these treatments, for each scenario, the amount of irrigation water applied was the same. So using this methodology, we basically built, some of these, scenarios. And then to decide optimum irrigation strategies, our considerations were either seed cotton yield or irrigation water use efficiency or crop water productivity. So there are different definitions for these, irrigation water use efficiency and crop water productivity. The one that we use for irrigation water use efficiency is the ratio of difference between irrigated and dryland yield and the irrigation water applied. And for crop water productivity, we divided, irrigated yield with the total water use, which includes rainfall, irrigation, soil water use, and capillary rise. So here are some of the results, that we presented, like published in this paper. You're welcome to, contact me if you need copies of these papers. I'll be happy to share. But when we look at here in all these analyses, what we did is, we ran the simulations for about 40 years, and then we divided them into dry, normal, and wet years based on the growing season precipitation. And then when we look at, for example, the normal years, for example, in all these normal or dry or wet years, when we look at distinctly, this pink line, which is basically a T4 treatment, where I mean, irrigation water was skipped in the peak bloom growth stage. So that performed poorly compared to all other strategies, indicating that the peak bloom growth stage is very, very critical in cotton, and then applying less water and that stage could drastically reduce the yields. That was the first clear cut distinction. And then the second one, what we can see here, in case of dry years, there is a constant increase in the irrigated seed cotton yield with the increase in amount of irrigation water applied. But in case of normal years, that kind of was there until S4, which is about 420 millimeters of irrigation water, and after that, the yields are almost like plateaued. So that means there's no additional benefit of applying more than 420 millimeters of irrigation water in such normal years. And in case of wet years, see, the curve is more flattened here, as we can expect, there was more water available through precipitation. So even after 360 millimeters of irrigation water, there is not much incremental benefit in yield by applying more water. So this is based on the seed cotton yield. Now, when we look at the crop water productivity, kind of similar trends, once again, the T4 treatment showed, low crop water productivity because, this is a function of yield and then the irrigation water application. So again, the T4 treatment, that means, the peak bloom growth stage was found to be very, very critical. And one more thing that we can see is, the black line, which is the T1 treatment, has been consistently, showed higher, crop water productivity as well as the seed cotton yield. So that means, if you have limited amount of water, you can skip irrigation in the first growth stage. Even then, you can achieve, higher yields because it's less critical for water. So using that kind of analysis, then we suggested what are the efficient irrigation strategies for normal years, wet years, and dry years. And as we can see here, for example, in a normal year, S4T1 is the ideal strategy, which is basically apply about 420 millimeters of water, and then you can skip irrigation in the first growth stage, and then you can distribute the amount of water as shown in this graph actually. So this is kind of way we built these studies and then made some useful recommendations for the producers. So then, as I said, we went on and then we did combine these growth stage based irrigation strategies with percent ET replacement based strategies. So what we did is, using the models capabilities. See, these are the advantages of models. We can run number of these such scenarios inexpensively and then very quickly. To do these kind of experiments in the field conditions takes several years, but the modeling is only complementary to field experiments, because without field experiments, without the data for model evaluations, we will not be able to achieve anything. So field experiments are gold standard, but the modeling is complementary, but it can be very, very useful to devise these strategies. So in this study, what we did is, we reduced, the growth stages into, 4. We combined the first, second into, the first stage here, just to, minimize the computational time. And then what we did is, in each of these growth stages, we simulated, 4 different, percent ET replacements, like 30, 50, 70, and 90%. And then we used 100% ET replacement in all growth stages as the baseline. So in this fashion, so we were able to build about 256, scenarios or strategies, and then compare their performance with reference to the control scenario. So what we found is very interesting. So once again, if we see here, this is the, the effect of irrigation water application on seed cotton yield in wet years, normal years, and dry years. And as you can see here, in the normal years, there is a steep increase in seed cotton yield until about, this 275 millimeters of water. And then, it starts plateauing. In case of dry land, there is still a potential to, get additional yield by increasing the irrigation water. In case of wet years, this flattening, happens much earlier as expected and as we have seen in, the other study as well. So when we look at the irrigation water use efficiency, once again, it continuously increased up to about 250, 275 millimeters of water, and then it flattened. Whereas in case of wet years, there is no benefit of applying more irrigation water beyond about 200 or 225 or something like that. So basically, then what we did is, among all these 256 scenarios, so we identified, the scenarios with more than 95th percentile, either seed cotton yield or irrigation water use efficiency. And then we look more closely into those, identified strategies to suggest, the best management, best irrigation strategies. So I'm in the interest of time, I'm not giving you all the details, but those are there in this paper. But as you can see here, finally, what we came out is like if the goal is to increase the yield, then it would be desirable to implement 90% ET replacement in the first three stages in the normal years, and then about 30% ET replacement in the four last growth stage. Likewise, you can see and if the goal is, to increase the irrigation water use efficiency, for example, see here, if you compare the difference, so in addition to this, it suggests you can reduce, the irrigation like into 50% ET replacement in the first stage, and then the last stage, and 90% ET replacement in the remaining two stages. So these are very useful, depending on the water availability, the producers or the well capacities, the producers can adopt, these strategies. And now with the, weather forecasts available, it's not very difficult to, predict, whether the upcoming season is going to be a normal season or a dry or wet season. So accordingly, these strategies can be implemented. So we did a similar study for sorghum, and I know this is a busy slide, but I can try to simplify here. So, for example, in case of sorghum, based on the sorghum yield, so these are the efficient irrigation strategies. And then here I want to highlight, these are the simulated yields, and then the values in the parentheses are for the control scenario, which is 100% ET replacement in all the growth stages. So you can see here the percent changes. Let's say, for example, by adopting this strategy in a dry year, the producers can, save irrigation water by about 10% by increasing the water use efficiency by about 4%. Of course, by losing, some yield advantage here. So likewise, we quantified, for example, based on the irrigation water use efficiency, these suggested strategies can save almost up to 25 to 40% of irrigation water. And such strategies are very crucial, for this region, where the declining water levels, restrictions on the groundwater use, and then, projected warmer climate are posing challenges. So then next, as I said, the science and, and we thought like, okay, the strategies that we suggested in the previous studies are, we have to choose whether the goal is based on yield or based on water use efficiency. Then we came out with this idea that, okay, can we do it a little bit differently? Like, for example, if one person, the goal may be maximizing yield, and the other person, the goal may be maximizing, yield, but while maintaining a balance. So then how can we prioritize, and then accordingly suggest, these strategies. So we developed a prioritization index ranking system, based on, a yield, crop water productivity, and irrigation. The way we did it is, we assigned, weights to these, three parameters. And then we scaled, these the three variables, between 0 and 1. So theoretically, this prioritization index, should range between 0 and 1. But the actual numbers, depended on the weights, we assigned. So the combinations we considered in this study are, first, the priority scheme was you provide, equal, you apply equal priority on, yield, crop water productivity, and irrigation. So if for someone who is more interested in yield and crop water productivity and less interested in irrigation, because maybe he has well capacities, which are sufficient, then, this scheme would be better. And then if the goal is, to get, or prioritize, crop water productivity and irrigation, then, this scheme would be good. And then we published this study, Professor Kanwar invited us to, publish an article in this Journal of Agricultural Engineering. And this was published in that study. Thank you, Professor Kanwar, again. So these are the results from that study. So what it says is, in case of dry and wet years, under all these prioritization schemes, these strategies are good. And then this tells us in comparison to the control, how these strategies performed. Basically, they can save up to 36% irrigation. In case of dry years, of course, by foregoing about 20% yield, but it would also increase the crop water productivity by 5%. But in case of wet years, so these are the results. In case of normal years, we found different strategies for different prioritization schemes. So the PS3, which is focused heavily on irrigation, so this strategy would save about 34% irrigation water, and by foregoing about 11% yield. So depending on the priority, one can adopt what is best based on their well conditions, their well capacities, and then expected yield goals. So now I want to spend a couple of minutes, a few minutes on the mobile app, that we developed, basically considering short-term weather forecasts. So our goal here was, to develop a mobile app which is inexpensive and easy to use, and which collects, the real-time information from the producer or the user, and combine it with historic and forecasted future weather data to basically generate efficient and situationally relevant irrigation schedules and estimate associated cotton yield and economic outcomes, so that the producer can choose a strategy that best fits their needs and their resource availability. So primarily we developed it for a center pivot irrigation system, but we are now seeking funding to apply to other systems and other crops, and then across the cotton belt. Actually, our proposals are under review. So in this prototype that we developed, we proposed two approaches. One is purely based on crop model-based irrigation scheduling. The other one is, both sensor and crop model-based, irrigation scheduling. And we published this study in a Smart Agricultural Technology Journal. You can review that, for more details. So the way this, prototype works is, what we did is, we utilized, the opportunity to, mount these sensors on the top of a center pivot, so that as the pivot, rotates, it can sense, the crop growth, the crop stand, and that information can be used in irrigation scheduling. So here we set up, a crop canopy sensor, a canopy temperature sensor on the top of the pivot. So as the pivot moves, they monitor, the crop growth. That information can be taken in the second approach, where we use the crop model and sensor-based irrigation scheduling. So the architecture is like this. What it does is, it uses the basic information from the producer, like, what type of soil, what type of cultivar they use, what type of tillage management they practice, the planting dates, and then the irrigation, water application, fertilizer, and chemical application from the user. So the user can input this information. And then we provided, for the benefit of the user, already 20, soil types, which are common in this region. And then 3 types of cultivars, the medium, maturity, long maturity, and early maturity cultivars. So we develop those cultivar parameters, and then we input them in the system. So farmer can choose which type of cultivar, which type of soil, and then enter information about the tillage, planting, and other things. This is an optional method, is using the sensors on the center pivot. So the way the model works is, in addition to this, the model the app is smart enough, to gather the information about the weather data from the on-site, or the nearby the NOAA weather stations, and then it combines it with the weather forecast, and then it inputs everything into the crop model, which basically estimates the irrigation water requirement and yield based on different deficit levels, 40, 50, 60, 70, 80. The farmer can choose whatever deficit they want to implement. So it basically displays, all these things on the mobile app. Okay, if you adopt this 50% ET replacement from now on, this is your expected yield, and this is your irrigation water requirement. And then, so as, for example, if the season becomes more wetter, the farmer can, move from, let's say, 60% ET replacement to 80% ET replacement, or, so likewise, they can either drop down or, increase, the percent ET levels, depending on the availability of water, precipitation patterns. So it's very useful, actually. So this has a number of features. So it enables producers to choose a strategy that best fits their well capacities and expected returns. It automatically integrates, weather and sensor data. It provides, the visual analytics that way, the easy for the farmer to decide. And then it interfaces directly with the DSAT model, which is, available on the server. And these can be done in both, the iOS and Android type of phones. And it also enables both online and offline usage. So in case of the sensor-based scheduling, what it does is instead of model deciding when to irrigate, we can use this canopy temperature data to estimate crop water stress index, which can be used to trigger irrigation, and then use the model to estimate the water requirement, and then display those strategies on the dashboard so that the user can make a decision that is best suits its requirements. So the most important thing in this is the weather forecast, outflow that we use. As you know, for a crop model, the weather data is the most important, the data. So what our app does is, it takes the historical and real-time weather data, if it is available on the, the farmer's field or nearby, the NCDC or NOAA, weather stations. And then it uses, the short-term weather forecasts, which are available for 16 days and updated daily, and then the seasonal forecast for up to 6 months, and then which are updated monthly. So as the new data becomes available, the model is smart enough, or the app is smart enough, to update the weather file and input to the crop model, which provides us the yield and seasonal irrigation water use, so that the user can select the strategy. And the another advantage with this app is, it also does the economic and risk analysis, and it uses enterprise budget, and then it provides several features. Basically, it estimates the gross revenue, total cost, and then it subtracts them, and then to get the net return for each of the strategy. So again, the producer can make a choice based on, the expected returns. So in summary, the region and crop-specific crop growth stage-based irrigation strategies, can be developed for different crops and different regions, even in India or anywhere in other Asian countries, to enhance water use efficiency while maintaining higher crop yields. So remember, these are site-specific because they are dependent on weather, they are dependent on the soil properties and things like that. But the methodology that I showed can be applied to anywhere. And then, likewise, one can use optimization techniques, and prioritize the decisions, whether, the goal is to increase yield or irrigation water use, or, the crop water productivity, or all of them, or some two of them. And then these irrigation decision support tools are very useful for precision irrigation application, and such tools can take advantage of projected short-term weather forecasts available online mostly. And then, but however, to do these kind of studies, the major challenge is availability of data for model evaluation. And I strongly, advocate, interdisciplinary collaborations. So especially in India, where I worked for 12 years, I see, those lines in between. Okay, this is agronomy, this is soil science, this is engineering. And without, the collaborations, such, multidisciplinary tools cannot be developed. For example, in our app project, we have agronomists, we have soil scientists, we have computer engineers. So such collaborations are needed to provide solutions, for these emerging, challenges. And I would like to acknowledge, these funding sources, and then the DSAT Foundation, for providing support for our project, the Cotton Incorporated Ogallala Aquifer Program, our university's, water initiative. And this is my, email address. Please email me if you need copies of these papers or any additional questions you may have, or, for potential collaborations. I thank you for your time. And at one last slide, I see, there's a lot of interest in regenerative ag, in this webinar series. So we are publishing a special collection of papers in ASABE. And if anyone is interested, please submit a manuscript to this special collection. The deadline is June 30th. Of course, there are publication charges, but there are some advantages. Like the first 3 pages are free, and first 3 years, the papers are available for free download for anywhere. So thank you again for your attention, and I will be happy to take any questions at this stage.
Thank you, Dr. Srini. And the queue, Dr. Gajan Singh, please.
Okay. Thank you, Srini, for excellent presentation. I have a query that how do you apply these restrictions on groundwater pumping? What kind of measurement systems you have? Because this may be very useful if we can tell that, okay, that's what nature gives us. And if that's what you have done, limiting 18 inches to a rainfall range of 15 to 20 inches annual rainfall. So I think Punjab, especially Rakesh Sharda ji, might be interested to look at how to put it on ground and monitor.
Thank you, Professor Singh. So it's not like here in the Texas actually. So there are groundwater conservation districts. So they implement these restrictions actually. So the High Plains Water District is the main the water district in the Texas High Plains. So what I mean, like these are actually the state agencies that implement these restrictions. So the way it is done is, the farmers are supposed to have water meters on their pivots or, the irrigation systems. And I believe, they have to report, to these water districts how much water was consumed or applied in a particular season. So it's not for our research purposes. We only, see how much is the estimated irrigation requirement, under each of these strategies, and to enable the producers to tell them that, oh, if you follow these kind of strategies, then the water application can be limited to within the available limit action. So it is imposed by the state, by the water districts.
Thank
Yeah,
you.
but I think it is very easy to measure the water meters on the pump. Huh? Mhm.
Yeah. So the government and the Texas Water Development Board, I think, subsidizes, those meters and encourages farmers to, use them on their pivot systems. It's basically, they subsidize, and then in return they expect the data to be given to them on how much, water they apply, and it is a regulatory.
Yeah, if we can put these water meters which people cannot manipulate, then only it will work.
Yes. Yes.
Okay, thank you. Mhm.
Thank you. Dr. Pitam Chandra.
Thank you, Dr. Smile. How do I spell your, or how do I pronounce your last name, Srini?
Srini.
Ale. Last name Ale.
Ale. Okay.
Ale.
Now you indicated that the amount of water you can predict from models, but how to apply? I could see only the overhead sprinkler system being used for application. Did it ever cross your mind whether you should try drip irrigation also?
Yeah, I mean, we can do these studies for other methods of irrigation also with this model. Basically, it's all like the irrigation efficiency is the important factor in that. So we need to change that depending on the method of irrigation. That way, based on the efficiency, the suggested or simulated irrigation schedules would be different.
Yeah, because Dr. Sharda indicated that in cotton, we could achieve 35% or 40% efficiency by using drip. Now here in your case, the amount of water to be used would definitely go down if we go for drip instead of sprinkler system.
Yeah. Yeah, and then in the Texas High Plains, actually the center pivot is very, very popular. It's almost like 70% of the irrigated area, or even 85, 75%, and then about 15 to 20% subsurface drip irrigation, is used. And now the area under subsurface drip irrigation is increasing, and then the area under center pivot irrigation is decreasing. And there is only like about 5 to 10% area which may be flood irrigated, like with the furrow irrigation and things like that.
So the trend is in right direction then. Thank you.
Yeah.
Thank you.
Thank you, Dr.
Suresh Kulkarni.
Yes, sir. Thank you very much. First of all, congratulations to the ISC committee for holding such a webinar on an important topic with experts from India and abroad. It was very, very technical and a lot of things to learn. I have some issues to just please forgive me if I say something, odd. See, Punjab in India, Punjab perhaps has the highest irrigated area in the country. Maybe the Haryana and Punjab close to 100%, maybe 90% plus.
Yeah.
So someone said that some area is facing the salinity and another area is facing the drought. So this is a very paradoxical situation in Punjab and similarly many cases. Now, I'm really wondering that we're talking Dr. Sardar because unfortunately I missed the earlier speaker's presentation. I really wonder that why we really concentrate so much on paddy using drip irrigation. Is it really we should go for drip irrigation in for paddy? And interestingly, I visited it because the person, Israeli person who was the pioneer who had invented. He said Uri Or, perhaps his name, and he came to Mumbai and he also made a presentation in here because
I would request
we,
you to make questions because a lot of people are waiting.
yeah,
Make
not
questions,
questions.
please.
Let me tell you. These are the questions. These are questions. Please try to understand. Have a patience. So end drip. I am talking about the end drip. End drip technology is very expensive. And we try to in Maharashtra also we try to use that
Dr.
technology.
No, Kulkarni,
It is-
Suresh, you
Yes,
ask
sir.
your questions instead of giving your
Okay.
talk because if you
Yeah.
ask questions, we are
Question
doing
means-
live. And if you want to participate in the webinar, we give some other time to you. Please ask questions.
Yeah. But see, my questions will be why not we are using AWD,
Thank you.
alternative water. This is much more easier for the farmers to use. That is one thing. And regarding the scheduling, already in Maharashtra, people are using the satellite remote sensing kind of a scheduling advices. So, are there such advices there in Punjab or some other places? Because in Maharashtra, people are using extensively
I have to interrupt you, Doctor
Yeah.
Suresh Kulkarni. I have to interrupt you because the question is very long. You're giving a lecture.
Yeah, just a small one. And okay, but I think if there is such no queries, then I have to stop here because
please, Rakesh Sharda, can you reply on why AWD is not taken?
The first thing is AWD. Now, if you are doing AWD, your power supply must be very disciplined, which is not the case because a lot of load shedding is there. Say I use AWD and suddenly I want to irrigate on a particular day, but then there is no power supply available. What I am going to do? The one thing. If the power supply is sufficient, it's okay. Now the other part was why drip for paddy? We are in the process where we say that, okay, we have to be future ready. But right now we are saying, okay, for first we go for 8 lakh hectare area only. But then to be future ready and to be water sustainable, we have to adopt such technologies. People are working on growing rice in hydroponics. That is the stage. And we also have to work on the similar lines and make the system less costlier. And regarding the end drip, the cost is around 60,000 rupees per acre for 2 feet, for the lateral spacing of 2 feet. That's what I have got. Thank you.
Thank you. Dr. Indramani, please.
No, I have very simple question. Srini, congratulations, and thanks for, making very good presentation on this AAA webinar series. Actually, I want to just have, we'll just discuss separately because our situation is same in Marathwada and the area which you are presenting. Crops are same. we would like to collaborate, with you. And my scientists have joined here. So I just wrote to them that we should work, with you to find a good solution for the same crop, cotton, sorghum, soybean, all these crop. And water situation is very, very, alarming here also. So this is the only, we want that we should have collaboration with you.
Yeah, thank you, Dr. Indramani. I'll be
Thank
happy
you.
to collaborate and then, help, your colleagues.
Yeah, yeah, yeah. Thank you.
Thank you. Thank you. Dr. Kotke?
Yes, thank you, Professor Srini. This was a nice presentation on modeling. In fact, in India, the modern soil water engineers are always blamed about the modeling. The modeling work results do not reach to the stakeholders. As far as your presentation is concerned, at the end you have shown the mobile app. Do you have any stakeholder farmer, because you have the center pivot system and other mechanized and automated systems? Whether you have any stakeholder at present, because I don't know whether your app is published and it is ready for the use.
Yeah. Thank you, Dr. Kotke. Yeah, actually, we only developed a prototype and then we tested it in, 3 farmers' fields. And, it showed, promising results in terms of saving water and all. So, as I said, like to expand this, for the entire region, and we are seeking, additional funding. We submitted a proposal. So once, we expand it and then, we are, it will be freely available actually to the producers in this region. So right now, we are at a stage where we developed and tested a prototype which works great. Yeah. We
Thank
did
you.
test it on the research field experiments and then, in the farmers fields. Yeah.
One another
Thank you.
small question. Just do you have any replacement for canopy sensor if the farmer does not have, or whether it comes with the center pivot system attached with it?
Yeah, I mean, that can be easily mounted on the center pivot irrigation system. Yeah, and but the canopy temperature sensor is very popularly used in this area. And then, the other sensors could be like sap flow sensors, that we are trying in a different project actually. Yeah. So the key is like IoT, like Dr. Sharda mentioned, like, communicating with these sensors and, the loggers and then, the decision-making systems is the key. So there are plenty of opportunities for our ag engineers, to get the advantage of.
I just want to add, Dr. Uday Kotke, the temperature sensor is IR based, like what they used in during lockdown period to measure your body temperature. They are available here. You can get for crop therapy easily here. Okay, next question is from Dr. TBS Rajput.
Dr. Srini, I must compliment you for really presenting a very detailed work and using almost all sorts of tools to come out on a good solution. But now my concern is the direction of the research. When we talk of irrigation scheduling, it is started with the IWCP ratio. It went to different growth stages, and that was in the 60s and 70s. And again, after doing all the procedure of FF56, calculating ET0, simulating the plant growth stages, simulating the total plant growth, and simulating the water requirement every day. Now you are getting back to the growth stage and applying water at different growth stage. Is there any special? I just can't understand. So should we go around like this, or should we take a direction to develop some solution? Otherwise, all the researchers will keep doing this.
Yes.
I am also one of them, so don't take it as a race.
Yeah. No, I
Okay.
take it positively. That's what I said, right? Like, I think, that integrating, the percent ET based with the crop growth stage based irrigation is the novelty, right? I mean, like they were there. That's what I told, like percent ET replacement and the growth stage based irrigation have been there. But I think the idea is like combining those two approaches to even save more water. And then, in this mobile app type of work, there it's a real time, Dr. Rajput. As I said, once we build this system, you know, everything goes in a real time. Like as the day passes, we have a new irrigation schedule, new irrigation, you know, I mean, like for different, you know, strategies. So it's again aiding producers to make decisions based on, you know, the resources available and then, you know, the projected weather data. I think that is another novelty is like, can we make use of these short-term weather forecasts to make better decisions actually? So um, I
Anyway,
think that
your work is excellent. Your work is excellent.
So I think I'll let that, Dr. Rajput. I think
Yeah.
after this webinar series over,
Yeah.
including you, we are all going to make a white paper and make a plan. I told
Yeah.
I told already people 10% water I want to be saved in 2 years. Okay.
Yes.
So at least take about 100 acres of land. We will do that. The
Yes.
census, everything required, I can really help you out, all the stuff.
Yeah.
We will do that. Then
I just want
one
to
more.
add one thing, Dr. Rajput, is like, you know, traditionally the soil water sensors have been extensively used. Now the direction is moving more into, you know, water stress sensors, you know, are the like, you know, the sap flow sensors, you know, the canopy temperature sensors. Even like now their canopy temperatures is less important. Sat flow sensors and other stress sensors have been becoming more popular, like, you know, and then with the UAV data, as someone was saying, like, you know, the remote sensing data, integrating those actually is also, you know, making ways. I mean, those are the new directions in which irrigation scheduling area is
Dr.
going.
Srini, we worked on the leaf area potential, we worked on the target pressure, we worked on the sap flow meters. What I am saying is that is for our satisfaction as a researcher. But what is the designed result for the farmer, for whom in the name of whom we are doing all this?
See, as I understand, Dr.
Yes.
TVS, everybody told, including you, we have to measure water.
Yes.
Number one. Okay.
Yeah.
Number
Yes.
two is what Rakesh Sharda told. Very easy to model it with only temperature, humidity, and probably pressure.
Yes.
We will
Yeah.
work on that. We have one more question. We have Dr. Sunil Gorantiwar, please.
Yeah. Yes, thank you very much. Though I missed the most part of Srini's lecture, but I have just two small questions. One is what would be the comparison of central pivot and linear move? And number two is that whether we can use the NDVI sensors actually. So those are becoming cheaper as well. So it will provide the what we call as the real time and site specific indicator as well. Yeah, thank you.
Yeah, those sensors can be also mounted on a linear move, you know, irrigation systems as well. And then, I mean, like as I said, like, you know, we are even moving into, you know, other methods of irrigation, like, you know, we can put representative canopy sensors at different, you know, places in the field, and then, you know, remotely monitor the data. And then to the what was the next question, Dr. Gorantiwar? Second one.
It was, Miss, one was how do you compare linear move and central pivot, and the second was how we can, whether we can use NDVI sensor actually.
Oh yeah.
So I think probably you answered both in.
Yeah.
Okay.
So the NDVI sensor actually, I mean, like it directly doesn't, you know, capture the stress. It only gives the growth, you know, the conditions, right? So I think NDVI can be used indirectly, you know, but not directly for irrigation scheduling, whereas the canopy temperature and then sap flow sensors can be used, you know, for irrigation scheduling because they are directly telling us the stress level in the plant.
Yeah, fine. Thank you. And just one information, we developed this weather-based and what we call as the soil moisture sensor-based IoT-enabled autonomous system. Maybe at some time, if I get opportunity, I will try to present those. And that is being also adopted by government of Maharashtra. And as far as the spectral response is concerned, we are also trying to narrow down the stress spectrum for different crops actually. Yeah, maybe we can discuss some other time. Yeah, thank you very much. Yes.
Okay, thank you. I will be in touch with you, Dr. Gorantiwar.
Yes, thanks a lot, sir.
I think I just want to add one thing, Dr. Ismail.
Sunil should make a presentation. Yeah, yeah.
Yeah, just I was thinking, like, you know, I really like, you know, the Dr. Rajput's comment about, you know, the practical utility, and then, you know, where are we going in terms of adoption and all. I know, even, there are a number of projects and schemes like, Spark and other programs, where they're encouraging, collaborations and all. But I think, what we are lacking is, maybe like, some kind of implementation, like, they follow up, basically, they're funding these projects and then they just get the reports and then that's it. And then what is that action, that is being taken at the end is more important, actually. See, the government is investing a lot of money. And then how is it converted into, usable tools? And then, the measures is where I think, we should focus on.
I think we
don't
have
worry, you will be
you're
called.
like-minded people here. Many of
Yeah.
them, I can see them, many of them same what Srini told. So we will do something change this time. I think we'll do. Dr. Indramani, if you can conclude.
Once again, thanks for the opportunity to, share some of the work,
Dr. Indramani?
Maybe he's not here.
Okay. He's there.
Is that?
Please, Dr. Indramani.
You're muted, Dr. Indramani.
Yeah, it was a very good session, and we are expecting another very important session tomorrow. And I request all the participants to spread this message, particularly Dr. Rajput Sahab, students should join, these. I am from Parmani, I have requested you. So please spread this to different groups, because new scientists and young scholars, research scholars should join this webinar. And thank you to both the speakers. Wonderful presentation. And AAA basically wants to take this, include more people. I have written to some more friends in US also, Dr. Indrajit Chaube and all, that they should come forward and make presentation. And here in India also. So hope Dr. Uday Khodke, you also plan, you have worked a lot in water management, and then Gorantiwar Sahab is here. So let's hope that this series will generate more interest, and we will, will be really doing, a good service to the profession. My only suggestion is that this should lead to some collaboration. This should, more togetherness, and as Sayyid Ismail is telling, some on some areas, some 100 acres or so, is telling, let us have, if we can get this technology. But Parvani will be one area where, one place where we can plan, at the.
We want Punjab. We want Punjab.
So
Dr. Sharda will arrange that.
Yes.
Yeah, sure.
Sidhu was ready.
He's a
Sharda
good
will
host.
make a big team and then do that.
Yeah.
Yeah,
with
sure.
this,
Always
with
welcome.
this,
Because everybody is
with this,
willing
thank
to
you
do
very
that.
much. With
Thank
this,
you.
thank you very much.
But-
We close the.
But even IRI farm is so big, I think certain things can be tried there.
Yes, sir. Yes. Why not? Water Technology Center, Dr. Rajput Sahab.
Yeah.
Water Technology Center doesn't have that much area with us. The total area is 18 acres only with the WDC. So
Yeah,
it
but
has
most
to
of
be.
the scientists are using flood irrigation or
Yeah, so
IRI
the
farm.
entire farm, of course, not adopting any water saving technique,
Yeah.
despite efforts of several people, including late Dr. Sira. We installed measuring devices in the scientist fields. They removed it. They don't know our crops will die.
I also remember visiting many universities, many research centers, and seeing all the drip irrigation systems lying idle. And some of them really, we will change now. The idea is many like-minded people. I think we all put our some effort, each one of us. I think we should be able to change the direction.
We are, sir, we are doing at Parvani under CSR funding. So
okay, good.
land irrigation have come forward, and 5-hectare area they adopted. They gave solar pumping, whole irrigation system, and pigeon pea. So new crops we are trying, and wonderful results are there. So what we are doing
Dr.
is,
Saeed, if we could find time, I would give you an example of my 13 years work in Alwar.
Yes.
Where I have been putting all my energies into the farmer's field who are having just half an acre each land. They are migrated
So
from
you make a
Pakistan at
presentation,
the time.
Raj.
Yes,
You make
I'll make a
another
presentation on
presentation.
that.
Yeah, why don't you
Yes,
make
I will.
another presentation? Because
Yes,
idea here is to bring the real practical solutions.
Exactly.
I'll discuss that someday. Yes, I will make a presentation.
And
I'll be in
farmer
touch with you. I'll be in touch with you.
Sure.
Professor Singh has given a very good idea. Somewhere, some success story of water saving in any
Yeah.
situation at farmer field.
It should be in the farmer's field, not
Yes.
in research station. This is what I want.
Yeah.
And like that's why I told you 50, 100 acres farm, not just 1 acre trial period. No, because some of the parameters we know already, we are confident. Why don't we try it out? That's my
Yes.
opinion.
Okay, thank you very
Okay.
much.
Thank you.
everybody.
Thank
Thanks,
all
everyone.
of you.
Thank you.
Namaskar.
Close the
Thank you very much.
See you tomorrow. See you
Thank you.
tomorrow
See you
at
tomorrow.
7:30, please.
Thank you, Deep. Bye, जी. Good night.
राकेश कल सुबह मिलते हैं.
हाँ जी सर, आ रहा हूँ.
हाँ.